Hello everyone, I'm Kang. I work with Jongmin Choi and Higa Ban. We are from Post-Tech, South Korea. In this presentation, I'm gonna explain about intersecting disks using two congruent disks. This congruent means that the two disks have the same radius. Before getting into the main subject, think about following question. What is the best location of two cafes in the university? It is easy to imagine that range of the cafes should cover all the buildings of university. This figure shows two cafes cover all the buildings which represent points. Now consider a more realistic case. If you want to consider the number of people in each building, then we can treat building as disk of which radius is the number of people in the building. Next case, what is the best location of two Wi-Fi routers? In this case, the range of routers should cover all the area of the buildings. So it would be better to consider boundary of buildings instead of points. Like these examples, if we can find the best location of facilities and compute size of the facilities, then we can cover all input objects and reduce cost of constructing the facilities. Like these figures, other facility location problem and clustering are also applications of our studies. Facility location problem is extensively studied in the computational geometry field, and clustering is used in many fields of the computer science. From now, let's get to the main subject. We study about variations of the Euclidean center problem. The definition of the Euclidean center problem is follow. Given a set of n points and find the center point Q such that minimizes maximum Euclidean distance between the input points and the center point Q. This is equal to the following problem. Finding the smallest disk C that covers every input point. Because the center of disk C is equal to center point Q of previous problem. This problem is optimization problem because we have to find the optimal solution. Euclidean K-center problem is variation of center problem. In the K-center problem, find K-center points such that minimize maximum distance between each input point and its nearest center point. This K-center problem is well known as NP-hard. We can find easily approximation algorithms and work on the case where k is small. In this presentation, I give algorithms for the variations of two-center problem. We studied about two-center problem on input disks and its variations instead of input points. First, we studied the two-center problem on input disks as follows. Finding the two smallest congruent disks C1 and C2 such that every input disk intersects the union of C1 and C2. In this figure, you can see every input disk intersects union of C1 and C2. Next is restricted to cover problem on input disks. This problem is to find the two smallest congruent disks such that every input disk is fully contained in one of the two disks C1 and C2. In this figure, you can see every input disk is fully contained one of C1 and C2. Finally, two piercing problem on input disks. This problem is to find the 2 points Q1 and Q2, such that every input disk is pierced by one of 2 points Q1 and Q2. To sum up, we study about these 3 problems. In the two-center problem, every input disk intersects union of C1 and C2. In the restricted two-cover problem, every input disk is fully contained in C1 and C2. And in the two-piercing problem, every input disk intersects Q1 or Q2. In this presentation, we focus on the two-center problem on disks. The algorithm of two-center problem also works in the restricted two-cover problem. The algorithm of two-piercing problem is a partial algorithm of two-center problems. There are previous work and our results of the two-center problem on input disks. Previously, An et al. Gave deterministic algorithm and randomized algorithm for the two-center problem on disks as follows. Our deterministic algorithm runs in n square log cube n over log n time, and our randomized algorithm runs in n square log n square over log n expected time, where n is the number of input disks. After this slide, we focus on the deterministic algorithm for the two-center problem on disks. We use a parametric search to obtain the deterministic optimization algorithm. The parametric search is a well-known framework that solves optimization problem. To apply the parametric search, we have to design a sequential decision algorithm and a parallel decision algorithm. There are 2 well-known techniques of parametric search: Megiddo's parametric search and Cole's parametric search. As you can see, the Cole's parametric search is faster than Megiddo's parametric search. But there is some requirements to apply the Cole's parametric search. In this presentation, I will skip details of this parametric search. So, we design a parallel decision algorithm that satisfies requirements of the Cole's parametric search. Our parallel algorithm uses more processors than previous work and need additional preprocessing, but this can improve total time complexity. We also design a faster sequential decision algorithm than previous results. Finally, we can get deterministic optimization algorithm that runs in following time. Now, I'm gonna explain what is decision algorithm and key point of our sequential decision algorithm and parallel decision algorithm. The decision problem is to solve the decision version of the problem. The decision problem is as follows. When given a real value R and disks, determine whether 2 congruent disks that intersects all given disks and its radius is given value R. Decision algorithm also determines whether given value R larger than R star, where R star is the optimal radius of C1 and C2. Like this figure, when C1 and C2 exist, then the given value R is larger than R star. In this case, C1 and C2 do not exist, and the given value R is smaller than R star. By those properties, we can get the optimal solution by applying parametric search. From now on, I will explain about how to determine the existence of C1 and C2. In the decision problem, we use inflated disks. The inflated disk is inflating radius of original disk by given value R. we determine whether intersection of inflated disks with R is non-empty, instead of finding disk with radius R. Let Q be a point in the intersection of inflated disks. Then, Q can be center of disk C with radius R. In other words, we can solve the decision problem by solving the piercing problem on inflated disks. So, we reduce the decision problem to the two piercing problem on inflated disks. Then, C1 and C2 exist in the decision problem if and only if Q1 and Q2 exist in the two piercing problem. Previous work also designed decision algorithm with this approach. From now, I will show that how to solve the two piercing problem on inflated disks. This is basic idea to solve the two piercing problem. This approach based on the previous results. First, divide the inflated disks into two disjoint subsets via criteria. To consider optimality, we consider all candidates that each represents one case of dividing. For each candidate, we compute emptiness test such that determine whether each intersection of disks in subset is non-empty. For example, we determine whether intersection of red disks and intersection of blue disks are non-empty. If there exists a candidate such that each intersection is non-empty, then Q1 and Q2 exist. In each emptiness test, we can determine efficiently by using a convex programming. To compute all convex programming faster, we store frequently used intersections in data structures. From now, I will give details of dividing criteria and data structures. As mentioned, we divide input disk sets via criteria. Our work used different dividing criteria from previous work. Previous work divided disk set based on inflated arrangement. This figure shows each point represents each face of the inflated arrangement. And previous work divided into two subsets by each point such that one is pierced disks by the point and the other is remaining disks. In this case, a red disk pierced by the point and blue disks are remaining disks. For this case, divided to two red disks and two blue disks. They only compute emptiness test with intersection of blue disks, because red disks are already pierced by a point. In our algorithm, we divide input disks by a line. The center points of red disks are lying under the line, blue disks are remaining disks. We compute emptiness test with each color. The number of candidates of both criteria is n squared. To compute all emptiness tests efficiently, both work construct data structures and store intersection of disks in the data structures. In the previous work, they define segments based on arrangement traversing. During the traversing, each disk may appear or disappear. When a disk disappears, then a segment appears until the disk appears. For example, see this figure. There is a segment S1 that does not include the disk D1. In this case, there are two segments S2 that do not include the disk D2. Using those segments, previous work constructs segment tree. For each node of segment tree, represents disks such that are not pierced during each interval. For each node, they store intersection of disks in the node and use the intersection in the emptiness test. There is a one-to-one correspondence between each leaf node and each face of inflated arrangement. This means each leaf node represents an emptiness test. So each emptiness test brings intersections in its and its ancestor nodes and apply a convex programming. In our work, we use following point line dual arrangement because there is a one-to-one correspondence between each candidate and each face of the dual arrangement. We construct a dual tree of the dual arrangement such that each edge represents one inserted disk. By this property, we do not have to compute the intersection of all disks in each node. For each node, we compute the intersection of disks in node but not in some ancestor nodes. We compute the intersection of log n exponential disks, then we can get log n array such trees. This slide is for details of log n array such trees. The log n array such trees is the collection of trees. For each leaf node of dual tree of the arrangement, we construct log n array such tree. For example, in this figure, there are 4 leaf nodes in dual tree, so there are 4 log n array such tree. Furthermore, we can avoid compute duplicate node by using pointer. Like previous work, there is a one-to-one correspondence between each leaf node and each face of the arrangement. So, each emptiness test brings intersections in its and its ancestor nodes and apply a convex programming. This slide is for compare previous work and our work. Previous work, insert or delete a disk one by one, but our work, only insert a disk one by one. So, we can compute the intersection of disks in node but not in some ancestor nodes, because ancestor nodes already store intersection of those disks. As you know, the height of segment tree is log n, and the height of log n array such trees is log n over log n. This means for each emptiness test, our work uses less intersections of inflated disks than previous work. This is overview of time complexity of the sequential decision algorithm. First, we can construct the data structure faster than previous result. Second, we use less intersections of inflated disks in convex programming than previous work. Finally, we use insertion-only convex programming instead of chance convex programming. This insertion-only convex programming is trivial technique, but it helps to avoid redundant operations. Now, I'm gonna present our parallel decision algorithm. This is overview of the parallel decision algorithm. As I say, we design parallel decision algorithm that satisfies requirements of the closed parametric search. It needs more processors and additional preprocessing, but improves total time complexity. In this presentation, I focus on the necessity of the sequential preprocessing. The key idea of sequential preprocessing is construct data structures only one time, because it is inefficient to construct data structures separately for each processor in the parallel decision algorithm. To avoid this, we design sequential preprocessing. First, construct data structures for all R value. We can construct these data structures by storing intersection of first terms instead of intersection of disks. Using this data structure, we find an interval in all R value, such that same order of arcs in any R in this interval and optimal value R star in this interval. Finally, construct data structures for this interval. Then, we can use these data structures in the parallel decision algorithm. Now, I'm gonna explain details of them. As mentioned above, we can obtain log-n-array search trees for all R value by storing intersection of first terms instead of disks. For example, this figure is an intersection of 4 first terms. In the intersection of first terms, we focus on order of arcs of common intersection. In the figure, common intersection consists of 4 red circular arcs. Let Ri be i's Rx value, which is order of arcs changes. Let's see the figure. There's one circular arc disappear at Ri, and all arcs disappear at Ri minus 1. Like this, we collect all Ri in log-n-array search trees for all R value, and find an interval by binary search. Finally, construct log-n-array search tree for this interval. Now, we already compute data structures in the sequential preprocessing. So, we only parallelize emptiness test. In parallel emptiness test, we apply parallel convex programming. It uses quadratic number of processors, but it can be improved total time complexity. For each emptiness test, use following processors. Now, we have sequential decision algorithm and parallel decision algorithms. So, we can obtain deterministic optimization algorithm by applying coarse parametric search. Furthermore, we can obtain randomized algorithm by using chance optimization. If determinator consists of constant objects, then we can obtain randomized optimization algorithm by using chance randomized optimization technique. The determinator of the two-piercing problem on disks consists of at most 6 disks. So, we can obtain randomized optimization algorithm that runs in following time. As mentioned above, our algorithm also works in the restricted two-cover problem by replacing definition of the inflated disk. We replace definition of the inflated disk as follow. Then, we can solve the restricted two-cover problem on disks with same time complexity. This is our conclusion. In the two-center problem and restricted two-cover problem on input disks, we improve more than log-n, log-log-n factor than previous results. In the two-piercing problem on input disks, improve log-log square n factor. Our future work is studying general two-cover problem on input disks. In general two-cover problem, find two smallest congruent disks C1 and C2 such that every disk is fully contained in union of C1 and C2. It is a little bit harder than the restricted two-cover problem. The algorithm of previous work slower log-n factor than the result of the restricted two-cover problem. Thank you for listening my presentation.